Today, our speaker is Matt Shatley. Matt is CEMA's database and systems developer, and he oversees the day-to-day operations of our systems and databases, but also develops and maintains much of our ingest processing and database code that enables CEMA to actually function. If you've seen it, touched it, it's probably had Matt's fingers pushing the data through. Matt completed his undergraduate work at UD with a major in computer science and completed his master's degree in our geography department, concentrating on machine learning. The title of Matt's talk today is Building Resilient Systems to Serve CEMA Data and Applications. And with that, Matt, over to you.
Yeah, thank you everyone for coming today. So as Tina already outlined, we're going to be going through a few different topics for this webinar, just to give you a general idea of the software and hardware required to keep data moving within CEMA. I'm sure everyone's come to our website for real-time measurements, but taking those sensor observations from the field to a system that makes them available for display, mapping, and just general analysis, it's actually a pretty complex process. We're going to do a quick overview of the data streams we take in. We're going to give an idea of the server infrastructure here at the university, and we'll finish up with just an overview of our database and web services. We're going to try and stay at a very high level view, avoiding as much jargon and just acronym soup that's kind of common within IT and system server infrastructure. So as covered in the developing and maintaining the DEOS network webinar, we have our stations deployed in the field with data loggers and cellular modems that allow us to store measurements and transmit data back to the university. Unfortunately, given today's operating environment, it seems like a data breach, system compromise, or ransomware attacks occurring almost every week, if not every day. So to combat this, we have a mobile VPN or mobile virtual private network set up for all of our stations. This allows us to segregate our stations from the rest of the Verizon network and the public internet. This ensures our systems can talk to one another. We can access data, we can work with our stations in a secure manner without having to worry about someone else connecting, trying to use our systems in a manner they weren't designed to be used. An additional benefit of the mobile VPN setup gives us a bit of redundancy as well. So when we go to communicate with our stations, we have a connection from the university to 2 different locations in Verizon's network to help minimize downtime if they were to run into any issues. Our local DEOS stations are not the only data source that we're handling. We also acquire data from various regional partners and national networks that take observations around Delaware. These data sets are downloaded via various services and APIs in many different formats. Unfortunately, it seems like every agency or organization has a preferred file format that needs to be manipulated before we can make the data ready for use. The timing of data updates is also very sporadic. It depends on the observing organization and the need they're trying to fulfill that dictates that observing frequency. The quality control, quality assurance needs of that organization also start to play a role here as well. For those that attended last week's webinar, some of those concerns and issues were covered for the DEOS network. If you missed that webinar, I believe a link will be available in the near future for that. Just as a refresher for everyone, we've pulled together a list of some of the observing networks we're acquiring data from and making operationally available. This is not a comprehensive list by any means, but it gives you an idea of the data being pulled into our systems. Keep in mind, each one of these partners is meeting a distinct observing need and distributes data in a different format. As you can imagine, we didn't start with all of these data streams on day one. This list has been growing as time goes on and different needs exist to acquire and offer new data sets out. Next year, we're going to be adding in real-time well data from the Department of Natural Resources and Environmental Control. So that's going to be another entry to that list that we're going to be maintaining and implementing. We don't just work with real-time environmental sensors, though. We also process modeled and gridded data sets like DBOFs, or the Delaware Bay Operational Forecast System, along with radar and satellite data. Radar measurements are usually acquired from Dover Air Force Base. I believe the sign is KDOX. But on occasion, we've had to switch over to one of the other radar installations in the area, just as maintenance would dictate for Dover at that point. The radar measurements have proven to be one of our more popular products on our website, with users telling us it's their go-to source during rainfall events. We're also working with satellites in real time or near real time, depending on the product and need. For instance, the GOES-R satellite provides an almost real-time feed of conditions on a roughly 5-minute update interval. So now we have an idea of what we're capturing. What do we do with all this data? Naturally, all this data is distributed to end users at some point or another. Our website provides an easy point of access for researchers and the general public. We're also providing data to the National Weather Service, with a key user being the National Mesonet program. This is in addition to our local weather forecast office at Mount Holly, New Jersey, and the River Forecast Center in the State College of Pennsylvania. We also provide real-time alerting system where we can send email and text alerts to public officials based on desired criteria. A good example for our alert system is our work with the pond monitoring stations. These stations take measurements of water levels at the ponds and lakes behind our state's high hazard dams. When certain criteria are met, emails and text messages are dispatched to state officials so they can monitor the water level and take preventative action, such as lowering the water level to prevent a dam from being breached or overtopped. Finally, our observational data can be used to calculate derived products, or decision support systems can be built to help visualize conditions which might require action. An example of this would be our water monitoring or drought detection work. So example of that is shown here. This plot combines observed DEOS precipitation data to show rainfall over the course of the year. The aim here is to visualize how much rainfall has fallen compared to a typical year and how much we're over or under so far. This plot is for Newcastle County, Delaware, but others are available for Kent, Sussex, and Chester County, Pennsylvania. We don't just aggregate the data at a county level, though. We're utilizing our DEOS datasets and other resources like an NCEP Stage 4 precipitation dataset to estimate precipitation at a high resolution for Delaware. Our dense network of DEOS stations also allows us to get a good picture of evapotranspiration conditions in the state, which is essentially the amount of water the environment is demanding. Putting the precipitation and evapotranspiration data together, we get the P-ET maps, which are shown on the far right here, which provide a decent representation of the surface water balance. The maps and graphs are used regularly by CEMA to inform the state about recent hydroclimatic conditions, which in turn informs water resource and drought response decisions in the state. We also subset data from GOES-R, the geostationary satellite. This is still a pretty good sized footprint for our area, but it gives us an idea of conditions in the Atlantic. During hurricane season, it's useful for tracking potential disruptions that could intensify into a named storm impacting Delaware. Additionally, this has been useful during poor air quality events seen during wildfire season, where the smoke and haze is actually visible from the satellite. We also have a smaller footprint focusing on the continental United States or CONUS with Hurricane Helene in the Gulf. I figured it would be interesting to show another example of our GOES work here. This product is similar to the approach of the Atlantic cover area, but we're also including data from the geostationary lightning mapper to show lightning discharges and storms as they move across the country. This is actually a pretty impressive system moving towards the coast. It's going to be quite interesting to watch in the coming days. So looking more locally, we have our radar measurements from Dover, which show precipitation intensity in the area. The radial velocity on the right shows wind movement away from the radar or towards the radar, with both of these helping to serve our severe weather monitoring and during significant storms. The base reflectivity layer is available on our homepage, and again, has been mentioned to us as one of our more popular products. So moving on to our infrastructure, we've tried to stay with freely available open source software as much as possible. We didn't want to buy into or be locked into any one path when we built out CEMA. One of the most common web development software stacks is commonly referred to as a LAMP stack. This stands for Linux, Apache, MySQL, and PHP. We use a modified version of this, which uses Oracle as our database platform now. Linux is known to be an open source, stable platform that can run for extended periods of time without issues or any downtime. Apache is a popular web server that runs a good portion of the websites on the internet, and is known to be stable and reliable, as well as open source and cross-platform. PHP is a cross-platform flexible programming language, which is known for its support of a wide range of databases that provides our backend and middleware capabilities. Some of you may be wondering, well, why did you choose Oracle for your database then? It's not open source, it's a paid commercial software package. Why aren't you in one of the open source, freely available databases? Well, for us, the university has a site license with Oracle, and it's running pretty well under Linux, and it runs under Windows as well. It's an enterprise-grade system guaranteeing uptime, reliability, and we also get support from Oracle to help maintain as much availability for the public as possible. It's worth noting all of these pieces are cross-platform, so if we need to change our operating system or our web server, that's all possible without having to make sweeping changes to our underlying workflow. Historically, all of our systems have existed at the university. We've had a pretty significant footprint when it comes to hardware, with servers for the database, web server, processing systems all being separate. The database server has always been one of our more capable machines, as it takes a good chunk of resources for a database system to operate efficiently and effectively at scale, given our size and activity. We also have a redundant database running in our server room, so if we ever had a hardware or software failure, we have a system that could step in and start serving data to users quickly. One of our only shortcomings on this front has really been our web server setup. We've been looking at adding redundancy to our web server configuration to provide that same failsafe, but for the time being, it's one of our single points of failure. I think it may be our only single point of failure left. In the event that our web server did go offline, we do have other systems that could step in, but it would require some downtime while we would make either a DNS change or bring it up into that role. Overall, we've tried to keep the web server configuration simple. So just as a worst case scenario, if we had to rebuild from scratch, it's going to be a quick and efficient process. It's not going to be very time consuming to stand that back up. Moving forward, we're going to be transitioning our systems to the cloud and trying to decrease our on-campus footprint. We've chosen to go down this path as the cloud claims to offer a good reliability and decreased administrative load due to the less hardware that needs to be maintained locally. With the cloud transition, the database is said to be available on a consistent basis, averaging about 2 minutes of downtime a month, which is pretty good. Additionally, the cloud is offering us some new capabilities to scale to meet user demand. If we have a significant event occur, say a major hurricane or snowstorm, the database can handle the increase in traffic with minimal changes, if any, required by us. A good example of this occurred a number of years ago during a major snowstorm. I think we were averaging about 30,000 hits over a 2-day time frame that really caused our server response times to increase. And it really highlighted for us the need to revisit some of our system design and figure out how to scale better to meet that user demand. As an added benefit, the cloud transition is going to allow us to run duplicate web servers more easily and better scale to meet user demands. Starting a duplicate web server can be done with just a few mouse clicks, so our recovery from a software failure can be dramatically reduced. Finally, guaranteeing data retention is absolutely critical. We back up our systems on a weekly basis and our databases more frequently. The cloud platforms are going to be performing daily backups for us, which simplifies our storage needs and complexity. The migration of the cloud is going to simplify the backup requirement for us just because we don't need to store those backups locally anymore. This further decreases our physical hardware requirements. So just to give you an idea, a typical full database backup for us is around 700 gigabytes in size. And you typically want to store a couple of full backups in case something goes wrong. Either the backup didn't complete successfully, a file got corrupted, the system just doesn't want to use it for some reason. So having multiple copies of this around does add up very quickly. Additionally, the cloud's going to allow us to run backup databases in different areas of the country or even globally if we wanted to go down that route. In the event of a major hurricane or natural disaster that would impact the university, we could begin resuming operations very quickly. As mentioned previously, we're using Oracle for its reputation as an enterprise-grade system. It's trusted by some of the largest companies to meet their needs. One of the selling points that Oracle gives us is it's almost a guarantee you will not lose data. Oracle databases provide quick and efficient data retrieval, but there's a bit of an overhead for running that enterprise-grade database platform. Overall, it's been fulfilling our needs well, and it's providing us with support if we run into issues, so it's been well worth the effort. One of the other database platforms on the market would probably work just as well for us, but given the size and complexity and the number of observations we've expanded to over the years, having an enterprise-grade system seems like a pretty good fit for us. We aren't exclusively an Oracle shop, though. We have numerous applications accessing data, running models, and helping inform users of conditions for their area of interest. So Kevin and Tina Callahan will be covering some of these applications in more detail at next week's webinar, CEMA Web Applications and Climate Services, if you're interested in more information. So we have the Delaware Water Quality Portal, which contains observations from numerous monitoring groups around the state. We ingest the relevant observations into a Postgres database that our front-end application accesses. So why do we go with Postgres for this system? Why don't we go with Oracle? Well, Postgres is an open source, freely available database system which is known for reliability. Overall, the Water Quality Portal is a small collection of observations compared to our main database. It's clocking in at around 300,000 observations from about 255 stations. The smaller data set size and less frequent updates of the data made that enterprise system just a little bit harder to justify the effort. The Delaware Irrigation Management System is another example of an application using Postgres for storage of user data. Most of this application is utilizing DEOS observations to calculate crop water demand, so the only real storage requirement is for the user's field information, such as location, planting date, and irrigation settings. The bulk of this application is the irrigation model running behind the scenes. That model is written in PHP, which was chosen as an open source flexible option with a wide range of database support. So that enables us, if we decided to change to a different database platform, we wouldn't have to make too many changes to our underlying code, if any. We also have our historical snow archive as part of our snow monitoring efforts. For those of you who are not familiar, some of our DEOS stations take real-time measurements of snow depth and report those for the general public and the state as part of the snow removal reimbursement program. The historical archive makes the official snow totals for each storm available for retrieval. During a typical winter in Delaware, we don't see a large number of snowstorms, so this is a pretty small database as well. Again, due to that size of the data, running an enterprise-grade system was a little hard to justify. Finally, we also have our coastal storm database and high watermark database that are being updated currently. Historically, these have been tracked in just a simple Excel spreadsheet. We hope to have these migrated into a database where users will be able to explore the data and we can build applications for those based on that information. We also have the Delaware Weather Hazard Index, which is an application where we're not using a database at all. We download model output from the National Digital Forecast Database and extract relevant predictions over the state. These observations then get summarized for quick display, but still maintain the ability to drill down based on users' interest. We also have a decent number of endpoints that provide access to data stored in our database or on disk. Historically, these services were all XML-based, but we've been migrating the bulk of these over to JSON or JavaScript object notation to make these a bit more modern. We try to provide enough functionality to enable web application development while also meeting the needs of stakeholders and the general public. This has been a bit of a challenge over the years as we've tried to support both worlds. As you can imagine, our desire to build an application or a decision support tool might require one format, while the general public would require another, and a funding agency might require a third format. It all depends on what their end goal is. One good example of this is the National MeasureNet program run by the National Weather Service. They're ingesting the DEOS network observations to provide initial conditions for numerical weather prediction models. The local forecast office is using these same observations as part of warnings and watches, but their systems are using a standard called UD CEMA, which is, you can guess would be a comma separated value format, which is going to be distinctly different from what a researcher or the general public might want to work with. So where are we going from here? Summing it all up, we're moving more of our systems to the cloud. This movement is going to allow us to revisit a lot of our code and build out systems in a more modern development architecture with more modern capabilities. Historically, we've tended to blur the line between development and tests. With the cloud options, we're going to be able to easily duplicate systems, including our entire database if we want to. We could spin up copies of systems to make adjustments. We could stage changes when a file format might be changing or a location for data needs to be shifted around. As part of our previously mentioned services rework, we're going to be examining our entire catalog of endpoints and how our users are actually accessing the data. We're hoping to make these more straightforward and faster for users while enabling new functionality. One aspect we're currently examining is enabling easier access for historic observations. So if a user came to the site and wanted to look at air temperature or precipitation in a past year, they'd be able to do that very easily and straightforward from the website without having to contact us directly. So with that, I'll open it up for questions, or if you'd prefer, you can reach out to us at cema-info@udel.edu.
Thanks, Matt, so much for your high-level overview of our systems. At this time, Chris, do you have any Q&A items that you'd like to bring up, or if you want to field other questions?
Yeah, Tina, I don't see any questions at the moment, but if anybody has any questions, let us know.
Okay, I'm not hearing any questions. And I guess what we'll do is ask you if you have any further questions that you think of later on. Feel free to give us an email at cema-info@udel.edu. You'll see that on the screen. And if Matt, if you can go to your next slide, just as a reminder that we'll be having our fourth and final webinar next Thursday at the same time, same bat channel. October 3rd at 1 p.m. Eastern. During this webinar entitled SEMA Web Applications and Climate Services, Kevin Brunson and myself will share with you value-added products that leverage DEOS and other environmental observing platforms, the role of DEOS in research, and weather and climate outreach services provided by SEMA in general. If you haven't registered for that webinar, you can find the registration link in the email, in the original email where we announced the webinar series, and or you can actually scan the QR code that you see right here on the screen, or you can also email us at cema-info, and we'll try to get you the registration link. So thanks again for your time and your interest today, and we'll hopefully see you next week. Take care.